Hi everyone. So in today's class, we'll be treating simple harmonic motion. It's actually going to be a very short class, but then hopefully there is no reason for us to like make it very long. Now, what's simple harmonic motion? Now, another name they always tend to call simple harmonic motion is oscillatory motion. Oscillatory motion, vibratory motion are kind of like simple harmonic motion. And simple harmonic motion is a motion in which the restoring force is very proportional to the development of the body. Now, this about from its main position. Now, this is just a this is just a formula. This is like definition of simple harmonic motion from the formula aspect. The definition, like the theoretical definition, is it is the motion of a body in which the body moves to and fro about a mean position. That's the theoretical definition. But then the formula definition is actually quite right as well too, because it's anytime you see any motion at all, that the restoring force is related to the displacement in that same direction, like the other motion to the restoring force, then that means that that particular motion is simple harmonic motion. So that's basically what I'm trying to say. And moving forward, so I hope you understand the fact that simple harmonic motion theoretically is the motion of the body in which the object moves to and fro about a mean position, while which relates to the formula that it must obey is that it's the restoring force is proportional to the displacement of the body. And you know that the restoring force is related to what? To acceleration. So you can say that the acceleration or the restoring force is directly proportional to the displacement of the body from its main position as well. Now, moving forward, the direction of this direction is always towards the main position. Yes. So the direction of the increase in the displacement is opposite to the direction uh, opposite the direction of the restoring force or of the acceleration of the increase in acceleration. So let's say, for example, in this case now, what this is saying is this. What it's saying is this. So I'll be using simple pendulum as an example. You have something like this, you have something like this, you have something like this. This is going like this. Now what this is saying now is that displacement is increasing towards this direction, x. So displacement x is maximum at this point. It's also maximum at this point as well too. Whereas the acceleration is in this direction. Acceleration is increasing in this direction. So that's why I said the direction, and acceleration is what related to what to restoring force. So the restoring force is in the opposite direction towards to the increase in the displacement. But then both of them are proportional to each other in terms of like magnitude. So that means the formula now becomes A proportional to what? Minus x, or F proportional to minus x. I hope you get that. Okay, so they've written the formula. So you have the acceleration and towards the main position. I forget to mention that sometimes that you actually take note. You should actually know when you are dealing with simple harmonic motion. You have the equilibrium position. Equilibrium motion is the state of rest. Is that point that the object is in when it's in the state of rest. So this is the equilibrium position. So any distance from this equilibrium position to any part of the body, like from here to here now, will be your displacement. So now the distance from this equilibrium position to the extreme end here is the amplitude, because that's like the maximum displacement. Amplitude is like the maximum displacement from the equilibrium position A. So my amplitude is in maximum displacement from the equilibrium position. Okay, so it said no, the acceleration of the particle executing simple harmonic motion is given by what? The acceleration, which relates to time t, is equal to what? Minus omega square xt. Now, the omega square is the constant there. You know, when you remove the proportionality constant from here, you have A equals what? K o minus kx. Now, that k is now what? Minus omega square. So that's how they got that in that particular case, in that particular scenario. Going back, so that's that, where the omega is the angular velocity of the particle. Now simple harmonic motion and circular motion are very much very similar in most cases. They are very, very similar. So now let's talk about some certain terms of simple harmonic motion. The first, you have your displacement. I already explained the displacement already. I explained the displacement. Is what let's start with equilibrium position. I already explained the equilibrium position as well. To what the main position is, like the undisturbed position of the object, like this position, the state of rest, like the position that the object is in when it's in a state of rest. That's the equilibrium position. And then the displacement is like distance from that equilibrium position to any point along the line. But more specifically, the distance from that equilibrium position to the maximum displacement that the object can ever be, like the maximum position that the object can ever be, is now your amplitude. And then we have, since we're dealing with simple harmonic motion, now simple harmonic motion is a periodic motion. When we were defining, when I was saying something about simple harmonic motion, I was saying that we're to and fro, like that shows what frequency. And then anytime you have frequency, you also have what period. Like show something that is rhythmic, something that is periodic, something that happens repeatedly. So you have a period and then you have your frequency. Now your period is the time taken for you to complete what one oscillation, and then one oscillation for a simple harmonic motion. One oscillation for a simple harmonic motion is to and fro. Take note. One oscillation for a simple harmonic motion is to and fro. For circular motion, one oscillation is from the starting point to that same starting point. So for circular motion, it's something like this. You have from here back to here, and it's also the same thing, like that same definition of period being the time taken for the object to move from a starting position back to that same starting position is applies to both. But then it might be a little bit confusing for some students because the way simple harmonic motion is structured. So most students might think, okay, the period is like from year to year. No, it's not. It's from year to year back to that same starting point again. So that's the period. Now, why the frequency is the number of oscillation that the objects undergo per unit time. So your period now, number of oscillation, your period T is your time taken to complete what one oscillation. So that's what total time over number of oscillation. Why your frequency now is total is the number of oscillations that can be completed per unit time. So what that means is that you have your n over your t. You notice that the relationship between the time and the the period and the frequency is more like inverse to one another. So that means the relationship between period and time will be what 1 over period is equal to 1 over f. The same thing as what frequency is also what 1 over t. Fantastic. So now these are the main things we'll be talking about in this class. The difference between simple harmonic motion, periodic, oscillatory motion, the types of different scenarios, cases of simple harmonic motion, some general terms, then some differential equation. I want to be emphasizing too much on that differential equation, then the angular simple harmonic motion, the quantitative part, and then the other important part as well too. Now, simple harmonic motion can be described as an oscillatory motion in which the oscillation of the particle at any position in the motion. We already said this. Now, take note. I was saying before that simple harmonic motion can also be said to be more like oscillatory motion. Now, oscillatory motion is the general name for simple harmonic motion and all other type of motion that are more like periodic. While specifically for simple harmonic motion, the acceleration must be proportional to the displacement from the main position. Now, all the simple harmonic motions are oscillatory and also periodic, yes, but not all oscillatory motion are simple harmonic motion. Take note of that statement. All simple harmonic motions are oscillatory and also periodic, but not all oscillatory motion are simple harmonic. Now, oscillatory motion is also called the harmonic motion of all oscillatory motion, wherein the most important one is simple harmonic motion. Okay. Now, there are some important terms we should probably take note of, like the displacement, the velocity, and then the acceleration. Yeah, that WRT, that W there is for the velocity, then the R is for, I think, the radius of displacement, and then the T is for the time or something. So now let's talk about the difference between periodic, oscillatory, and then simple harmonic motion. Oh, we already talk about that. It's more like this, more like just emphasize on some of them, or some key points. So if you really like want to like know more details and know the differences, you can just pause this video and then you just take note and just compare it. So our advice is that you actually like bring out your notes and then draw a table. Write periodic motion in one one column, oscillatory motion in another column, simple harmonic motion in another column, and then try and look for differences between each and one of them and the unique features of each and every one of them. So moving on now, conditions for simple harmonic motion. You have what we already said before, that the force must be the starting force must be equal to, must be proportional to the displacement, but then it's always in the opposite direction to it. So we have types of simple harmonic motion, two types. We have the linear and then we have the angular. Now the linear, when the particle moves to and fro from a fixed point, the fixed point is the equilibrium position, also referred to as the main position, along with a straight line, then its motion is called what? Linear simple harmonic motion. So what that means is, example of that case is loaded spring. A loaded spring, so it moves up and down. Like basically, if the part of the stuff is like in a straight line, up and down, then it is linear simple harmonic motion. But then if it's curved, if it's angular like this one of simple pendulum, then it is what? Angular simple harmonic motion. So basically, you have a lot of different cases of simple harmonic motion. You have simple pendulum, you have loaded spring, you have displaced test tube. Like you have loaded test tube. You have quite a number of them. Okay, yeah, these are some of the mean position. I already talk about the mean position. And acceleration at the main position is usually, now depending on the direction in which the object is actually facing. Let me use simple harmonic motion. This is becoming like too jam packed. So from here to here to here. Now x is maximum here. Acceleration at this point is in this direction. Acceleration at this point is in this direction. Take note of that. So that means acceleration here, and at this point now moving up. So acceleration at this point start going. Take note that we are calling the force or the acceleration restoring acceleration. So it's trying to bring it back to its main position. So that means the direction of the acceleration and the restoring force will always be towards the equilibrium position, towards that center. So if the object is here, the acceleration will be towards the middle. If the stop is here, the acceleration will be towards the middle. Now, while at this point, acceleration tends to be zero, although not actually zero, because when the object is, it's at the middle, at that equilibrium position, the acceleration is zero. In a non-disturbed state, let me add that. In a non-disturbed state, acceleration is zero at that middle position. Okay, I talk about the amplitude as well too. I talk about the period as well too, but I didn't talk about these 2 pi nu. Okay, let's talk about the period. It's about the formula for period. Now, as I said before, that the period is like the time taken for it to actually move to and fro about a main position. It's the time taken for it to complete one oscillation. And one oscillation is referred to be 2 pi. So one oscillation is what? 2 pi. And you have the angular period, the angular velocity. What am I saying? The angular velocity. This is, you have angular velocity to be omega. Angular velocity to be omega. Now velocity, and then the number. Like you have the velocity, then the 2 pi, which is the number of oscillation, is more like referred to be as the angular. Is more like the angular representation of the distance covered by the object undergoing that simple harmonic motion. Now for circular motion, now we know if the object is one that is undergoing that circular motion, and then angular displacement covered by the object is what the angle suspended at the center. So we are more like representing or equating angular velocity. I want like equating angles the um to more like the distance covered by the distance moved by the object, the displacement of the object in simple harmonic motion. So we are saying that for one complete oscillation, it is what 2 pi. One complete oscillation is what is 2 pi, and we are looking for what period is what time taken for it to complete what one oscillation. Now we know that okay, the angular representation of this is 2 pi. Now the time, we have the angular velocity also to be what omega. Don't forget that angular velocity omega is equal to what angular displacement over what over time. Now this time is what we are looking for. Time is the period, so we have time to be equal to what theta over omega. Now your theta is a 2 pi. Refer to this all over what all over your omega. So that's the way you calculate what your period. Your period is equal to 2 pi over omega. Let's see. Okay, yes, fantabulous. So that's your period. Now, taking that, we already said that the frequency is like opposite of what of your period. So you just reverse it and then you get your answer. So now there are different phases in simple harmonic motion, because now this thing is periodic. Anything that is periodic can be represented using an angular, can be represented using all this sinusoidal function and cosine function. So for displacement, we have x equals to what the amplitude, because now the amplitude is more like shows us the position that the object is in relative to the mean position. Like it's like you have from here to Sokoto, like let me use it from here to Sokoto. Let's say from Ibadan to how am I using Ibadan? For like let's say from Ibadan to Lagos now is a fixed distance. Yes. Now if someone is staying within, like the person is not going to Lagos, but then he's staying like probably in Ogun State now, a place that is between Ibadan and Oyo, so you can use the distance from Ibadan to Lagos to actually really to gauge the position of the person. You don't really know the person's distance, but then you don't really know the person's position exactly, but then you know distance from where the person, from that place that the person is going to Ibadan, or from that Ibadan to from that place to Lagos. So you can use the relationship between the two to actually gauge where the person is located. I don't know if you actually get it. Like you have, let me use the diagram. Okay, it's like you have from here to here now. This is the amplitude. Now, if the person is here now, you can use the relationship from between this point to this point. You can use the ratio to actually gauge where the person is. So you know that distance from here to here, let's say it's 5 meters, and then the ratio between this distance and this person is like, this is like 2. The ratio is like 2 to 4. So you can use that 2 to 4 to actually get, oh, what is that person's distance exactly? So let's say maybe the ratio between this and this is like 2 to 4. So that means, so that would be like 2 over 2 plus 4. That's like 6 times 5. That will give you the distance that the person is, like the person's position exactly. I hope you get that. So moving on. So that's why we are using like amplitude in that case. And then you have sine omega t plus phi. That phi is the what is the phase difference. That phi is the phase difference. The phase difference. Phase difference. Okay, as I said, now the phase difference is like, now phase difference is, now when an object is undergoing simple motion, it's not like doing the same thing over and over and over and over again. So what actually allows you to actually know the person's position is the phase difference. Because let me use this as an example. Let's say someone is going like this, palm, palm. The person is going. Now the person's position. What we trying to talk about? Okay, yeah, phase difference. Now, the phase difference is more like the position relative to a particular point. Like the position relative, like if I, now you know that the total stuff is like 2 pi. Now phase difference is more like what fraction of that 2 pi is the person found. Like what the person has is, like the object is within, is undergoing that simple harmonic motion. Now what points along that pathway is the person located? That's where you have your phase difference. Is the phase that the person, that the object is actually in, is actually located at that particular point. So that's like the phase difference. So now you can know whether the stuff is in phase or out of phase depending on what you have. Now if the object is in phase, you have n pi. Is that it can be that be zero. Like the stuff is now, and don't forget that when we were dealing with circular motion, we said all this phi and 2 pi can be represented with, can be said to be equated to like angles. So 2 pi is 360, pi will be 180, pi over 2 will be 90. So all these ways you know, oh yeah, the object is yeah. So it's always more like a fraction, more like a fraction kind of stuff. So for an object to be in phase with the object, it has to have a whole number, pi. So you have something like, it has a whole number or an even number. Let me use that. It has an even number of pi. So even number is like an whole number of pi. It must have an whole number, like 1 pi, like n pi. Now that's n pi. It must, when you calculate the phase difference, it must give you n pi. It must give something like n pi. While for when it's out of phase, it is 2n plus 1. So that means it most likely give you an odd number. So most likely give you an odd number. Maybe this other one too won't give you another number, but it will give you like an extremely like odd number. So I think we already talked about that. Okay, let's talk about the acceleration. Let's talk about how to calculate the acceleration of the restoring force. Let's talk about how to calculate the acceleration of the restoring force. Then we give the different scenarios of simple harmonic motion. You talk about the energy, and then we are Gucci. We talk about some very important formula. Okay, what's the first thing we should? Okay, now the acceleration first. Now let's know that the acceleration is proportional to what? Minus x, and when you remove the proportionality sign, you're going to get minus kx. Now, how do we get this kx? How do you get that k? Now, the k can be gotten from we have different cases of simple harmonic motion, and those different cases of simple harmonic motion gives us an indication of give us a value for k, specific value for k. Like for simple pendulum, now our k is g over L. So that will be what? Minus g over L x. I hope you get. So it's more like the specific case that you're dealing with that actually gives you an indication of k. But then the formula that you should actually put at the back of your mind is this kx. Now with that said, now let's talk about what else to talk about. Oh, now take note of this formula. Now this formula is very important. So you have, for angular displacement, theta equals t naught, that's like the amplitude, sine omega t plus phi. Now this phi is another formula used to calculate this phi is what? Is kx, where x is what? The amplitude is the displacement, y k is the constant, and you already know how to calculate the constant already. So take note of this formula. Now after taking note of this formula, then you can just substitute all this theta and other quantities with any other thing like angular displacement. It can now be this displacement function. Yeah, I think you can change it actually, because we always tend to we're always looking for the displacement. Basically, we are not always looking for the okay, we already try to like look for the velocity too at any point in time, but then once you know the displacement at that point, you know the location of the object at that particular point, then you can use that to calculate the this you can then use that to calculate your velocity. Okay, so this is where they got their k. Now this k over m is for what's this thing called? Okay, it's omega nth. So basically they were basically just playing with they're basically just playing with the formulas here. You have ma to be equals to kx, and then they make case of the formula, so it becomes k over this, and then the and then it said just km over a to be omega square, so omega will be equals to root k over m, and then from there you're just basically just playing with the formula here. So you can just pause this video and then go through the differential equation. You will most likely not be asked the differential equation. What you are concerned about is what is here, f equals to ma, and then a equals to minus k over mx, yeah, and then omega equals to root k over m. Those are the important things. You don't need to know the differential equation, how to derive the differential equation. So these are different differential equations that you have, and then the important part is the third one: x equals to a sine open bracket omega t plus phi. And don't forget I told you that phi is equal to what is kx. So I can see that they're basically just repeating almost like the same thing. Okay, now take note of this. Take note of what this relationship, when x is maximum or is negative towards the negative side, acceleration is maximum, and etc. Just take note of this formulas. Pause this video and go through this. You can even write it out so that it will stick better. Are you done? Now let's move on. Now take note of this formula for calculating velocity at any point in time. So you might be asked that what is the velocity when the element is so, or when the object is so distant from the equilibrium position. So the formula I'm going to use to calculate that velocity is what is this: v equals to omega square root of what, a square minus x squared. Take note of that formula. Take a very good note of it. Look at your Vmax. Vmax is what? At Vmax, and you already know the relationship here at this particular point in this table, that when v is maximum, then that means your x is your 0. So that means you come back to this formula and you have what? V equals to what? Omega root a square minus what? 0 square. So you are going to have your V max to be equal to what? Omega a. Take note of all those. Okay, you already know how to calculate I already talk about the formula to calculate your period. You already know the relationship between the acceleration as well too. Acceleration is always equal to minus omega square x. So just look for the position of the x, and you know how to calculate your x. Your x is like the distance from the equilibrium position to what? To that particular point that the object is in. That particular position that the object is in. Minus omega square x. Okay. And talk about the energy. This energy is like very, very important. Talk about the energy. Now, you know we have majorly in this, we have two major forms of energy: the potential energy and the kinetic energy. You know that your kinetic energy is related to what? To the speed or the velocity. Why the potential energy is related to what? To the position, to the like the height and all the counters. So your potential energy will be maximum when your position is maximum, like x is maximum at its maximum things. Why your kinetic energy will be maximum when your velocity is what is maximum. So coming back to this table, slot all those things in. Coming back to this table, and slot all those things in, and then you get your answer. So when x is maximum, potential energy will be maximum. Okay, the table is already even here, sir. Now let's talk about the energy exchange. Now the energy exchange is where the stuff comes from, and the way you when you solve questions, you understand it better. Now, but then let me just emphasize. Let me just explain on this a bit. Now, for energy, there is always exchange of energy between the potential, like interchange. The energy, potential energy is always like changed with the kinetic energy. Like you always like change it from one to another, from one to another, and you have to really be, and in order for you to actually know how much potential energy you have at this point, how much kinetic energy you have at this point, you have to be able to calculate the hex. Once you are able to solve your hex, then you can use your hex to calculate your V, and then when you calculate your V, you can calculate your maximum V once you know your your amplitude, and once you calculate your maximum energy that the object can have at all, and you are able to calculate the energy that it has at that particular point, then you can know the energy that it lost that belongs to the potential energy, and then the energy that the amount of energy that possesses the kinetic energy. So basically, be able to, like, once you know the formula, or you've mastered the formula for calculating your velocity at any point along the path of that object, then and you know your Vmax already. Like this is what it's in. Your kinetic energy is always equal to your potential. Like your kinetic energy maximum, your maximum kinetic energy is always equal to your potential energy maximum. But then it's just that at different points in time, the stuff changes. So let me use. I don't know why I like using simple pendulum. Now at this point now, V is maximum. So that means your kinetic energy will be what? Will be maximum here. Why at this point your V is 0, your potential energy will be maximum here. Same thing here. Your potential energy will be maximum here. So what that means is that along as this object moves from this Vmax now towards this side, you have the kinetic energy reducing. Now the kinetic energy is not being lost. The kinetic energy is being converted to potential energy. So if you can calculate your Vmax and you calculate your maximum kinetic energy here, so your maximum kinetic energy here will be what? You calculate your maximum kinetic, no, your kinetic energy at this point, or the potential energy at that point, will now be what? The maximum kinetic energy minus the kinetic energy at this point. So that'll give you what? Your potential energy at that point. I hope you get that illustration. Okay, so that's basically what I'm like talk about. Okay. Okay. Now this formula for calculating your total and mechanical energy. Mechanical energy is both the potential energy and the kinetic energy. And as I said before that when V is maximum, what the body has is only kinetic energy. When position is maximum, what the object only has is potential energy. So you can even calculate the total mechanical energy without even like using this formula per se. Once you are able to identify, when you're able to like calculate your maximum kinetic energy. So just take note of this formula. Pause this video and take note of this formula. And this is the diagram. This is a very fine diagram that shows you the relationship between the potential energy and the kinetic energy. When the potential energy is low, the kinetic energy is maximum. That's the way it goes, up and down, up and down. That have been changed. Okay, as I said before, that simple harmonic motion can be related to circular motion. But in class where we start solving questions, I will then emphasize on this. See you guys. This will be all for today's class. So see you guys in the next class.